According to the National Electrical Code, specifically Section 250.187, bare copper or aluminum conductors are permitted for grounding, which includes grounding electrode conductors and equipment grounding conductors, and bonding in underground or under slab raceways. Isolated or jacketed grounding conductors are also permitted. To reiterate, bare or insulated grounding and bonding conductors shall be permitted to be run in underground or concrete-encased raceways or embedded in concrete. The reasoning behind this is that the more restrictive rule requiring W-rated conductors for wet locations does not apply to underground or underslab raceways. These raceways are not considered wet locations as defined by the NEC because they are typically not exposed to continuous moisture. Bare grounding conductors are often used outdoors in direct contact with earth because they provide a low resistance path for grounding and fault currents. The same principle applies to using bare grounding conductors in underground or underslab raceways. When installing electrical systems, it's crucial to adhere to the NEC guidelines to ensure safety and compliance. The NEC provides specific requirements for grounding and bonding to protect people and equipment from electrical shock and fire hazards. The use of bare grounding conductors in underground or underslab raceways is addressed in NEC Section 250.118, which outlines the acceptable methods for grounding and bonding. Grounding electrode conductors, or GECs, connect the electrical system to the earth, providing a path for fault currents to flow back to the source. Equipment grounding conductors, or EGs, connect non-current carrying metal parts of equipment to the grounding system, providing a low impedance path for fault currents. Bonding conductors connect different metal parts of the electrical system together to create a common ground potential. The NEC allows bare copper or aluminum conductors to be used for grounding and bonding in underground or underslab raceways because these conductors provide a reliable and effective grounding path. The use of bare conductors can also simplify installation and reduce material costs. However, it's important to ensure that the bare conductors are properly sized and installed according to the NEC requirements. The NEC specifies the minimum size of grounding and bonding conductors based on the size of the overcurrent protective device in the circuit. The conductors must also be protected from physical damage and corrosion. In addition to bare conductors, the NEC also permits the use of insulated or jacketed grounding conductors in underground or underslab raceways. These conductors provide an additional layer of protection against corrosion and physical damage. Insulated grounding conductors are typically used in areas where the soil is corrosive or where there is a risk of physical damage to the conductors. When using insulated grounding conductors, it's important to ensure that the insulation is suitable for direct burial and that the conductors are properly protected from damage during installation. The NEC also addresses the use of concrete-encased electrodes, also known as U-for-grounds, for grounding electrical systems. Concrete-encased electrodes consist of a bare copper conductor encased in concrete, typically in the footing or foundation of a building. These electrodes provide a very effective grounding path due to the large surface area of the conductor in contact with the earth. The NEC allows concrete-encased electrodes to be used as part of the grounding system for buildings and structures. When installing concrete-encased electrodes, it's important to ensure that the conductor is properly sized and installed according to the NEC requirements. The conductor must be at least 20 feet long and must be encased in at least 2 inches of concrete. The conductor must also be accessible for inspection and testing. In summary, the NEC permits the use of bare copper or aluminum conductors for grounding and bonding in underground or underslab raceways, as well as insulated or jacketed grounding conductors. The NEC also allows the use of concrete-encased electrodes for grounding electrical systems. It's important to adhere to the NEC requirements for grounding and bonding to ensure safety and compliance. Always consult with a qualified electrician or electrical engineer to ensure that the electrical system is properly grounded and bonded. The key takeaway is that underground and underslab raceways are not considered wet locations in the context of the NEC, which allows for the use of bare grounding conductors. This allowance is based on the understanding that these raceways, while potentially exposed to moisture, are not continuously saturated in a way that would necessitate the use of conductors specifically rated for wet locations. The provision in Section 250.118(7) explicitly permits bare or insulated grounding and bonding conductors in underground or concrete-encased raceways, reinforcing the permissibility of using bare conductors in these scenarios. This consideration helps to simplify installations, reduce material costs, and maintain effective grounding systems. Understanding the NEC distinction between different types of locations, such as dry, damp, and wet, is crucial for selecting the appropriate wiring methods and materials. Dry locations are not normally subject to dampness or wetness. Damp locations are partially protected locations under canopies, marquees, roofed open porches, and like locations, and interior locations subject to moderate degrees of moisture, such as some basements, some cold storage warehouses, and similar locations. Wet locations include installations underground or in concrete slabs or masonry in direct contact with the earth, and locations subject to saturation with water or other liquids such as vehicle washing areas, and in unprotected locations exposed to weather. The NEC provides detailed guidance on the types of conductors and wiring methods suitable for each of these locations. For example, in wet locations, conductors must be listed and identified for use in wet locations, ensuring that they are capable of withstanding the effects of moisture and corrosion. This requirement is typically met by using conductors with a W suffix in their designation, such as THWN or XHHW. These conductors have insulation that is specifically designed to resist moisture and provide reliable performance in wet environments. However, as previously discussed, underground and under-slab raceways are not typically considered wet locations, which allows for the use of bare grounding conductors. When installing electrical systems in or under concrete, it's important to consider the potential for moisture and corrosion. Concrete is a porous material that can absorb moisture from the surrounding soil, which can lead to corrosion of metal components. Therefore, it's important to use corrosion-resistant materials and wiring methods when installing electrical systems in or under concrete. The NEC provides guidance on the types of materials and wiring methods suitable for use in concrete. For example, the NEC requires that metal conduits and raceways installed in concrete be protected from corrosion by using a suitable coating or by encasing them in concrete with a minimum thickness of 2 inches. The NEC also requires that grounding and bonding conductors installed in concrete be protected from corrosion by using a suitable coating or by encasing them in concrete with a minimum thickness of 2 inches. In addition to corrosion protection, it's also important to consider the potential for physical damage to electrical systems installed in or under concrete. Concrete can be subject to cracking and movement, which can damage electrical conductors and equipment. Therefore, it's important to use wiring methods that are resistant to physical damage and that are properly supported and secured. The NEC provides guidance on the types of wiring methods suitable for use in concrete. For example, the NEC allows the use of rigid metal conduit, intermediate metal conduit, and rigid non-metallic conduit for wiring installed in concrete. These wiring methods provide a high degree of physical protection and are resistant to damage from cracking and movement. The NEC also requires that wiring installed in concrete be properly supported and secured to prevent damage from movement. In summary, the NEC permits the use of bare copper or aluminum conductors for grounding and bonding in underground or under-slab raceways, as well as insulated or jacketed grounding conductors. The NEC also allows the use of concrete-encased electrodes for grounding electrical systems. It's important to adhere to the NEC requirements for grounding and bonding to ensure safety and compliance. Additionally, it's important to consider the potential for moisture, corrosion, and physical damage when installing electrical systems in or under concrete. Always consult with a qualified electrician or electrical engineer to ensure that the electrical system is properly designed, installed, and grounded. When dealing with electrical installations, it is essential to understand the different types of grounding conductors and their applications. The NEC recognizes several types of grounding conductors, including grounding electrode conductors, equipment grounding conductors, and bonding conductors. Grounding electrode conductors connect the electrical system to the earth, providing a path for fault currents to flow back to the source. Equipment grounding conductors connect non-current carrying metal parts of equipment to the grounding system, providing a low impedance path for fault currents. Bonding conductors connect different metal parts of the electrical system together to create a common ground potential. Each type of grounding conductor has specific requirements for sizing, installation, and protection. The NEC provides detailed guidance on the selection and installation of grounding conductors to ensure safety and compliance. For example, the NEC specifies the minimum size of grounding electrode conductors based on the size of the service entrance conductors. The NEC also requires that grounding electrode conductors be protected from physical damage and corrosion. Similarly, the NEC specifies the minimum size of equipment grounding conductors based on the size of the overcurrent protective device in the circuit. The NEC also requires that equipment grounding conductors be installed in the same raceway or cable as the circuit conductors. Bonding conductors are used to connect different metal parts of the electrical system together to create a common ground potential. This helps to reduce the risk of electric shock by ensuring that all metal parts are at the same voltage. The NEC provides guidance on the types of metal parts that must be bonded together, such as metal conduits, metal enclosures, and metal equipment. The NEC also specifies the minimum size of bonding conductors based on the size of the circuit conductors. In addition to grounding conductors, the NEC also addresses the use of ground fault circuit interrupters, or GFCIs, for protecting people from electric shock. GFCIs are devices that detect small imbalances in the current flowing through a circuit and quickly interrupt the power supply. GFCIs are required in certain locations, such as bathrooms, kitchens, and outdoor areas, where there is a higher risk of electric shock. The NEC provides detailed guidance on the installation and testing of GFCIs to ensure that they are functioning properly. In summary, the NEC provides comprehensive requirements for grounding, bonding, and ground fault protection to ensure safety and compliance. It's important to understand the different types of grounding conductors and their applications, as well as the requirements for GFCIs. Always consult with a qualified electrician or electrical engineer to ensure that the electrical system is properly grounded, bonded, and protected from ground faults. The information provided in the NEC is intended to protect people and property from electrical hazards. By following the NEC guidelines, electrical systems can be installed and maintained in a safe and reliable manner.